steel plate, CDE, is rigidly welded to a disc of radius 420 millimeters, which may rotate about its center O. At the instance shown, the assembly has an angular velocity of 5 radians per second clockwise and is decelerating at the rate of 10 radians per second square. Determine at this instant A, the angular velocity and acceleration of the assembly. B, the velocity of points A, B, D, and E. And C, the corresponding acceleration of these points. Let's start with the question E. What is the angular velocity and acceleration of the assembly? The angular velocity and acceleration is given in the problem. The assembly has an angular velocity of 5 radians per second clockwise and is decelerating at the rate of 10 radians per second square. The word decelerating means the direction is opposite to the velocity. The angular velocity is clockwise. The angular acceleration will be anti-clockwise. Now let's see question B. The velocity of point A, B, D, E. In this case, you are going to solve one by one. So let's take point A. Point A is this one. It is 350 millimeters from O. When the disk is rotating, there will be a tangential velocity at A. The tangential velocity at A will be directed to the right. The velocity of A is omega times the distance from O to A, 5 radians per second times 0.35 meter. So the answer is 1.75 meter per second. We know that the velocity to the right, so I draw arrow to the right. You can write in vector form 1.75 I meter per second. That is the velocity of point A. The velocity at point B, that is omega times the distance from O to B. Velocity at B is the same everywhere in the perimeter of the disk, except the direction changes. VB, with the same formula, you obtain the value and the angle direction. This angle is 90 minus 75, 15 degrees. Or you may write like this, a vector representation. Next is the velocity of point D. Since all parts of the rigid body move with the same angular velocity, it means the formula to calculate the velocity at D will be the same. It is omega times the distance. If you draw a line from O to D, the direction will be perpendicular. You know the height here, 380 millimeters. You know the distance from O to the projection of D to the x-axis. It is 420 plus 320. So you know this angle. Knowing this angle, you will be able to know what is this angle or the vertical angle. The velocity of D is omega times the distance from O to D. And the distance from O to D, you just calculate. So VD, you obtain 4.15 meter per second. If this is an angle phi, the angle will be 27.18. So if this angle, we call it beta, beta will be 90 minus phi. The velocity is 4.15 meter per second and directed 62.82 degrees to the right downward. Or you can write again in vector form. Point E is symmetrical to point D with respect to x-axis. The distance from OE will be the same with the distance OD. In terms of magnitude, the velocity at E will be the same with the velocity at D. Still the same formula. You calculate the distance. Say this one is gamma. Say this is angle delta. Delta will be 62.82 degrees. That is the answer. Or you can write in vector form. Question C. If in question B we ask about the velocity, in question C we ask about the acceleration. It is easier to write in terms of tangential and normal because we have rotation. Normal is always towards the center of rotation. For example, at A, we have the tangent to the right in the I direction. Normal will be from A to O. Tangential is vector product of alpha with R, or alpha R times the tangential unit vector. Normal component of the acceleration is omega, vector product omega, vector product R. Since you know that the direction of the normal is always directed towards the center, at A, the direction of the normal will be from A to O. At B, the direction of normal will be from B to O. At D, direction of normal will be from D to O. You see, all towards the center. On the other hand, we know that the R is always from the center going out. RA is from O to A. RB is from O to B. RD is from O to D. So it means the vector R is always opposite to the normal vector. Because of that, this formula we can write like this. Omega times omega, that's omega square, multiply with R, but R is always going out, but the direction of normal is going in. So I put negative. Or if you prefer to use UN, the unit vector in the normal, so it will be omega square R UN. That is the acceleration. So at A, it means the acceleration tangential is going to the left, and then the normal component going to the center. At B, the direction of tangential component will be directed to the right downward. And the normal will be directed towards O. At D, you connect the point O and D. We have calculated the angle previously, 27.18 degrees. The tangential will be perpendicular to that, directed upward. That is the perpendicular. So that is ADT, the tangential component. The normal will be directed towards O. And then point E. That is the perpendicular. That is the tangential component, and then the normal. Point A. A is alpha R. So this is the alpha. This is the R. The R is the distance from O to A, which is 0.35 meters. So you have the tangential component of point A. The normal component, omega square times R. This is the magnitude. This will be the resultant. The angle will be normal over tangential. The angle will be 68.2 from this horizontal line. Point B, you calculate tangential alpha times R. This is the alpha, this is the R, the distance from O to B. And for normal, the same thing, omega square times r, and then you can calculate the resultant and the angle. Point B, same thing. Okay, that is about tutorial 1. Only one problem.